It's the number of protons inside an atom that makes each element different. If we look at the periodic table, the first element, hydrogen, has 1 proton. The second element, helium, has 2 protons. And the third element, lithium, has 3 protons. That's right, 118 protons in its nucleus. Now, electrons are much smaller than protons, and they zip around protons at lightning speed, making up something called an electron cloud around the atom. Electrons do this because they have a negative electrical charge, which always pulls towards the proton's positive electrical charge. This pull between the positive protons and the negative electrons is called the electric force, and it's always there. So whenever a free electron gets close enough to a lonely proton, zap, they'll become part of the same atom. So why do atoms need neutrons? Well, without neutrons, the electric force will cause the positively charged protons to push each other out of the atom. But there's a stronger force that exists between neutrons and protons, which stops the protons from flying apart. It's called the strong nuclear force, or strong force for short. And it kind of works like glue to hold the nucleus together. If there were no neutrons, everything would simply be hydrogen.
E equals mc squared. You hear it all the time, but what does it mean? During his study of special relativity, Albert Einstein found that mass and energy are equivalent and that they could be converted back and forth between one another. He described that relationship mathematically, saying that the energy of a particle is equal to its mass times the speed of light squared. This mass-energy equivalence is critical to the study of nuclear physics, the study of the atomic nucleus. This is a branch of physics that introduces you to 2 of the 4 fundamental forces. One in which an element can turn into an entirely different element in just an instant, and one that has allowed us to unleash the incredible energy that's contained inside every atom. Before we can dive into the wonders of nuclear physics, we need to recall a little bit about the thing that makes it all tick. The nucleus. The nucleus of any atom consists of protons and neutrons. The proton is positively charged while the neutron is electrically neutral, and both particles have nearly the same mass. With the exception of hydrogen, which only has a single proton in its nucleus, every element has both protons and neutrons. Because of this, we'll often refer to the 2 particles collectively as nucleons. We can describe how many protons and neutrons are in an atom's nucleus using its atomic and mass numbers. An atomic number is how many protons are in a nucleus, which also determines what element the atom consists of. The mass number, meanwhile, is how many protons and neutrons combined make up a nucleus. So if there are 6 protons and 6 neutrons in a nucleus, then its atomic number would be 6, making it a carbon nucleus. And the mass number would be 6 plus 6, which is 12. And if there were 6 protons and 8 neutrons, then it would still be a carbon nucleus, but with a mass number of 14. Let's put these carbon nuclei in nuclear notation to better show the differences between them. First, we start with the chemical symbol for the nucleus.
Stars are made of an almost incomprehensible number of particles, which gravity compresses into a super dense core. This core is hot and dense enough to force atomic nuclei together, forming larger, heavier nuclei in a process known as fusion. The reverse process, where one atom splits into 2, is called fission. In both processes, the mass of the end products is slightly less than the mass of the initial atoms. But that lost mass doesn't disappear. It's converted to energy according to Einstein's famous equation. And since c squared is such a massive number, both fission and fusion generate a lot of energy. In the most common pathway, 2 protons fuse to form a deuterium nucleus, which then fuses with another proton to form a helium-3 nucleus, which then fuses with another helium-3 nucleus to form a helium-4 nucleus.
This process is referred to as nuclear fission. So, a process in which heavy nuclei are bombarded with neutrons and split into two equal masses, releasing enormous amounts of energy, is called nuclear fission.
A strong nuclear force holds the positive protons and neutral neutrons together in the nucleus, and is what determines, but not all nuclei are stable. Unstable nuclei either have too many protons or too many neutrons, upsetting the strong nuclear forces. Unstable nuclei try to balance themselves by giving off the excess proton or neutron. This is radioactive decay. Unstable nuclei are radioactive and emit radiation. There are three types of decay: alpha decay, beta decay minus, or beta decay plus.
Classification of elementary particles. Elementary particles can be grouped into two broad categories, fermions and bosons, based on the property called spin, which is connected by the kind of statistics the particles are governed by. Almost all elementary particles spin about the axis, and its unit is h cross, where h cross is equal to h by 2 pi. Particles which have odd half integral spin are called fermions, and those which have integral spin are called bosons. These fermions obey Pauli's exclusion principle. That means no two identical fermions can occupy the same quantum states. Also, these fermions obey Fermi Dirac statistics. The wave function which describes the fermions is antisymmetric. In the case of bosons, the bosons are not constrained by Pauli's exclusion principle. That means the number of bosons in any quantum state, in any given quantum state, is not restricted. These bosons obey Bose-Einstein statistics. The wave function of bosons is symmetric.
How do the positively charged protons in the nucleus stay together, since particles of the same charge repel each other? The answer is the strong nuclear force. There are four fundamental forces in the universe: the gravitational force, electromagnetic force, weak nuclear force, and strong nuclear force. Unlike gravity and electromagnetism, we can't directly observe the weak and strong nuclear forces in nature, since they're effective only at the subatomic scale. Let's compare the relative strength of the fundamental forces by assigning 1 to the force of gravity. We get this table. As you can see, the strong force is by far the strongest of the four fundamental forces, though its range is only about the width of the nucleus. When the protons in the nucleus approach each other more closely than a femtometer, that's 1,000 trillionth of a meter, the strong force becomes active and holds the protons together, since it's many times stronger than electromagnetism. So, atomic nuclei and atoms can be formed.
Dapat diketahui dan ditemukan fakta bahwa masih ada struktur yang lebih mendasar atau fundamental dari subpartikel seperti proton atau neutron itu sendiri yang disebut dengan quark. Quark sendiri sebenarnya telah diperkirakan keberadaannya pada 1961 oleh fisikawan Murray Gell-Mann tentang fakta kemungkinan adanya partikel yang lebih dasar dari proton dan neutron. Sebuah pengamatan pada hamburan inelastis yang dihasilkan ketika proton dibenturkan atau collider di akselerator partikel. Pengamatan tersebut menemukan pada hamburan inelastis mereka menyebut itu sebagai hadron, di mana hadron proton tersusun dari up quark atau quark naik dan satu down quark atau quark turun yang diikat dengan gluon sang pembawa gaya, sedang neutron terdiri dari dua down quark dan satu up quark kebalikannya, juga diikat oleh gaya yang disebut dengan gluon. Quark sendiri terdiri dari 6 jenis, yaitu up atau naik, down atau turun, strength atau aneh, charm atau pesona, bottom atau bawah, dan top atau atas. Quark merupakan partikel paling dasar atau fundamental. Selain keluarga quark, keluarga lepton juga disebut sebagai partikel paling dasar. Dalam keluarga lepton terdiri dari 6 jenis, yakni elektron, neutrino, muon, neutrino, tau, dan tau neutrino.
A lepton is an elementary particle and one of the fundamental building blocks of matter in the standard model of particle physics. Leptons are a type of fermion, which means they obey Fermi-Dirac statistics and obey the Pauli exclusion principle. Leptons are characterized by several key properties. Spin. Leptons have a spin of 1/2, a fundamental property that contributes to their intrinsic angular momentum. Charge. Leptons have electric charge, and there are 2 types of leptons based on their charge: charged leptons and neutral leptons. Charged leptons. These are negatively charged leptons. The most familiar charged lepton is the electron. These are electrically neutral leptons, and the most well-known neutral lepton is the neutrino. Neutrinos come in 3 types: electron neutrino, muon neutrino, and tau neutrino. Leptons are unique in that they do not experience the strong nuclear force that binds quarks together to form protons and neutrons. They only interact via the electromagnetic force and the weak nuclear force, making them relatively non-interacting compared to other particles. Leptons play a crucial role in various particle interactions and are involved in processes such as beta decay, where a neutron transforms into a proton, emitting a beta particle, electron, and an antineutrino, a type of neutral lepton. The conservation of lepton number is an important principle in particle interactions, stating that the total number of leptons minus the total number of antileptons remains constant during certain interactions. Leptons, along with quarks, contribute to the diversity of matter in the universe and are essential components of the particle zoo described by the Standard Model.
If you've had any interest in physics at all, you've heard about a thing called the Higgs boson. But just what is it, and why is it interesting? In 1964, a physicist by the name of Peter Higgs took some ideas that were floating around at the time, added an insight or 2 of his own, and proposed that there was an energy field that permeated the entire universe. This energy field is now called the Higgs field. The reason he proposed this field was that nobody understood why some subatomic particles had a great deal of mass, while others had little and some had none at all. The energy field that Higgs proposed would interact with the subatomic particles and give them their mass. Very massive particles would interact a lot with the field, while massless particles wouldn't interact at all. The lightest of the familiar subatomic particles is the electron, while in the subatomic world, the king of mass is the top quark. It weighs about as much as an entire atom of gold, about 350,000 times more than the electron. I'd like to stress that we believe the top quark is not more massive because it's bigger. It's not. In fact, we believe that both the top quark and the electron are exactly the same size. Indeed, they both have 0 size. The top quark is more massive than the electron simply because it interacts more with the Higgs field. Actually, if the Higgs field didn't exist, neither of these particles would have any mass at all. The Higgs boson is the smallest bit of the Higgs field. To understand how that works, we should again return to water. Everyone knows what water is. If you're immersed in it, you know that water is everywhere. It's a continuous medium, and there are no holes in it. We also know that water is made of molecules, specifically H2O. If you hold these 2 ideas in your head with the realization that water consists of countless individual molecules, you can now begin to appreciate the Higgs boson. The Higgs field that gives subatomic particles their mass is made of countless individual Higgs bosons, just like water is made of individual molecules. You should keep in mind that the Higgs boson hasn't been discovered yet, and what I'm describing is simply the most popular idea as to why subatomic particles have the masses that they do.